guess, in
We will
Indonesia.
start soon. We will start soon. Good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for joining in room 5. In this room, we are going to have invited speaker session, and then after the invited speaker session, we will have the oral presentations taught by presenters in this room. Firstly, I would like to thank Professor Mark Andre Gutstier for accepting our invitation to be invited speaker in this event. Thank you, and thank you for all the presenters that also have joined in our event. Firstly, I would like to introduce our invited speaker today, Professor Mark Andre Gutstier. Pardon, excuse me if I have the wrong pronunciation of your name. So Professor Mark Andre Gutstier graduated from University of Montpellier, and she is a department chair of Research Lab Geoscience Ocean since 2017, and then since 2000, he is a senior CNRS senior researcher. Topic says seismicity and tectonics of subduction zones. Okay, is it right, Professor Mark Gutstier? Okay, this is a brief introduction about the Professor Mark Andre Gutstier, and his publication. You can find a lot of his publication about the topic great earthquake and tsunamis, tectonics, and also mapping active faults. Okay, and today Professor Mark Andre Gutstier will present about the monitoring an active submarine fault using a 6-kilometer long fiber optic strain cable, the focus experiment. So you have 10 minutes. You have 20 minutes. You have 20 minutes to present your topic, and then after your presentation, we will have 1 or 2 questions from the audience in this room. So, Professor Mark Andre Gutstier, the time is yours.
Thank you, and thank you for having invited me to participate in your multidisciplinary research conference. So I'm going to be presenting findings from a European Research Council funded project called FOCUS, whose purpose was to try to detect movements on the seafloor due to tectonic faults using a fiber optic strain cable. Drat, it's not advancing, which means I'm going to have to quit this mode. That's what I was worried about. Okay, I'm sorry. That's maybe down here. There it goes. Perfect. Okay, so can you see the second slide?
Not yet. The slide is not moving yet on my computer. So this is the first slide with your title.
It's still the first slide. Okay, I think I've had this problem before. This is annoying. And it is not the first time that this has happened. So what I'm going to do is move back into here. And now you can see the second slide, but not in presentation mode. I'm going to make it as big as I possibly can. And with a little luck, we'll say that it's going to be enough. So you can see it in presentation mode. It's about as big as I can make it. And now I will start sharing again. Here, share screen, that one, and let's go. Okay, so with some luck, you can see that slide. This is an image of the European Mediterranean region. The plate boundary between Africa and Eurasia is shown here. And the study area that I'm going to be talking about is in southern Italy, off the island of Sicily, in the middle of the Mediterranean. And here we're at a plate boundary between the African plate, which is moving generally northwestward, and the European plate. And there's a very small subduction zone. And we're kind of at the edge of the subduction zone.
Excuse me, Professor Mark Andre. I don't know if the trouble is on my computer or another or others, but I can't see your screen sharing. Okay, it's fine now. It's working. Okay, thank you.
Okay.
Yeah, it's working now. Yeah.
Ooh, wait, that was strange. Okay, let's try this. All right. So now this is a closer up view of southern Italy, the Sicily Calabria area, which has been struck by strong earthquakes in the historical past, magnitude 7 and superior. And in the past 500 years, these earthquakes and tsunamis have unfortunately caused 200,000 victims. The most recent worst event being the 1908 Messina event, which killed 72,000 people. And there was the 1693 Catania event, which killed about 40,000 people. So these are, for European standards, very strong, very deadly earthquakes that occur in this region. And one of the problems is that the faults are slow moving and most of them are offshore. And so they're very difficult to monitor and already to detect these faults. And so that's why we're trying to apply a new technology using fiber optic cables to detect movements of faults on the seafloor. This is a view of Catania. It's a city in Italy. It's just on the foot of Mount Etna, which is the tallest and most active volcano in Europe, over 3,300 meters high. And this is the deep domain over here in blue. And there was an existing 29 kilometer long electro-optical cable, which the Physics Institute had installed down to here, down to Test Site South, leaving Catania and going down to 2,000 meter water depth. And it's on this cable that I was able to connect a new 6 kilometer dedicated strain cable. If you can see the cursor here. To the right, you see two images of seismic profiles crossing this fault. The fault is the North Alfeo fault. It starts, well, depending starting and stopping, it is the offshore extension of a series of dextral strike-slip faults on the southeast flank of Mount Etna, which are allowing the volcano, the eastern flank, to slowly slide into the sea. And these faults connect offshore to become one major strike-slip fault system. And here you see images of seismic profiles through that fault, and you can see that the reflectors are disturbed at a vertical limit, which is the strike-slip fault. Okay. The method I'm trying to apply is called BOTDR. That means Brewin Optical Time Domain Reflectometry. This is commonly used to monitor large infrastructure, things like pipelines, tunnels, bridges, dams, cooling towers of nuclear power plants, those sorts of things. And it can have it's very sensitive, and you can detect small strains of like less than a millimeter at very large distances, several tens of kilometers, if your fiber is well coupled to the structure you want to monitor, that you're trying to examine. And so you can do this very well in bridges or pipelines. It's more difficult on the seafloor. What happens is you send light down an optical fiber, and it bounces off imperfections in the optical fiber, and it is recorded by the interrogator. And there's three different kinds of phenomenon. There's Rayleigh scattering, which is sensitive to short-term strain, so vibrations. There's the Brewin optical time domain reflectometry, which is sensitive to long-term strain and to temperature fluctuations. So it gets heated or it gets cooled, and that causes thermal expansion or thermal contraction. And then there's Raman, which is sensitive only to temperature. And so here we're doing the Brewind. And in October of last year, so about a year ago, we performed this experiment, the starting part of this experiment, using the French research vessel Pourquoi Pas, leaving from southern France, from Toulon. And we used the unmanned submersible, an ROV, which means remotely operated vehicle, the Victor, the ROV Victor 6000. There you see it on the deck of the Pourquoi Pas. You can see some people, so you see the scale. It's about the size of an automobile or a small bus. And it can go down to 6,000 meters, and it has robotic arms, and that's what helps us do the work on the seafloor. Here on the left, you see an image, a 3D image of the relief of the seafloor with Mount Etna, the big volcano, in the background. In gray is the multi-beam coverage we did with the Pourquoi Pas vessel arriving on site. And you can see that curving line, that's the dark gray line, that's the fault. And then that little colored patch is a region where we did micro bathymetric mapping using the ROV Victor, and which you see there to the right. And so there to the right, you can see the trace of the fault going up here, just like that. In the south, there's a little transtensional graben. And up here in the north, there's a pop-up, a transpressional pop-up. And then between them, there are some little splays. And the next slide will show you the interpretation of that microbathymetry. So this is the main fault expression over here. And the seafloor observatory is kind of just off the screen here to the right. You can see them in a miniature image here where it is. So the seafloor observatory that we were connecting to is about 2.5 kilometers from the fault. And then with the 6-kilometer long cable, which you'll see very soon, we were able to cross the fault several times. To the left is the multi-beam coverage from the vessel with the microbathymetry as that little square, that little white square. This is the optical chain back in Toulon on dry land before we deployed it. There's a Y junction box you see here to the left. That's where we were able to connect to the seafloor observatory. There was a cable and module, which is affixed to our deep sea plow. And on the deep sea plow, on that reel, is the 6.2 kilometers of fiber optic cable. And here you see a cross section of the cable. It's 9 millimeters in diameter. There are 3 fibers in the core. They are tightly in a tightly bound configuration. And then there's 2 fibers in a stainless steel tube on the outside, and they are in a loose configuration. So 5 optical fibers. And this is the image of the ROV at the moment of connection, where it is connecting with the umbilical, an ODI wet mate connector, a teledyne connector, into the port C. And from the moment that it pushes in, then there will be an optical connection all the way down the full optical path. This is the deep sea plow going down on the off the back deck of the vessel with the cable and module and the 6 kilometers of cable here. This is the plow on the sea floor. This is the moment we were deploying the cable end module, which initially was attached here, and then we folded out and disconnected, and then it stays in place next to the Y junction box. And so we left from the upper right here, went along this portion here where the seafloor is pretty flat. Then it got much more steep and rugged with some east-west oriented gullies, which made the work very challenging. We crossed the fault once, twice, 3 times, 4 times. And because this is a dextral strike slip fault, that means the upper right portion here is sliding to the lower right. So the northeast section is sliding to the southeast with respect to the southwest block. So that means there will be elongation here, shortening here, elongation at the 3rd fault crossing, and a little bit of shortening at the fourth. That's what we should see if the dextral strike slip movement does what I just explained it should do. This is an example of the plowing after the work. To the left, the plow was able to successfully bury the cable about 20 centimeters below the seafloor. To the right, where the terrain is very rugged, there's basically like a cliff. Here we could not bury, and we just had to climb up over the steep seafloor. As I was saying earlier, there's 5 fibers, and because we only had access to 2 live fibers from the observatory, we made loops. So one pathway goes out along the tightly bound core and back through the loose fiber on the outside. And then the other pathway, and this is the one I will show you some data from, goes out through the loose, back through the tight fiber, and back out again through another tight fiber. So to the upper left, you see the interrogation, the laser interrogation, before we connected our 6-kilometer long cable with the plow. And so we can see out to the end of the existing cable, that's 29 kilometers in length. And the image in the lower left is just a couple hours later. They're from the 16th of October of last year, right after connection, right after the moment the ROV pushed in the connector. And so now we can see the 6 kilometers loose, the next 6 kilometers tight, and the final 6 kilometers of tight. And this is while the cable is still in the reel. And then a few days later, once the cable has been deployed, this is what the baseline signal looks like. And then what we will do is baselines to the initial baseline to see if there's been any change in the situation. So to the lower right, you can see the strain between the 28 October baseline and the 8th of November. So that's 11 days later. And because that's a very short period, we did not expect any movement. And on the left, you see the scale in microstrains. And basically, if nothing has moved, then the data should be giving a reading very close to 0. And that's what they're doing. And now the next images I'm going to show you are a zoom of our 3 segments of 6 kilometers of this portion here of the graph. So this is a zoom of the 8th of November of last year. And you can see that the data measurements are providing numbers roughly between 5 and 10, maybe 15 positive and negative microstrains, and they're oscillating above and below the 0 line. So there's been no strain between the 28th of October and the 8th of November. The next image I'm going to show you is from the 1st of May. Now you can see that on the 1st of May, a peak shows up here, and here, and here. And I'm going to go back. Oops, that didn't work. Sorry, go back. So 1st of October, 8th of November, 1st of May. 8th of November, 1st of May. So this peak is located 2.5 kilometers from the Y junction box. And that is the position where the first fault crossing is reached. So we are observing elongation at the first fault crossing. We're also observing a signal less strong, but still detectable at the third fault crossing. And here, these white triangles you see, those are seafloor geodetic stations. I'll explain that a little bit later. So once again, this is the signal of the 3 portions of 6 kilometers. The first portion, the loose. The second portion, the tight, coming back. And then the last portion, the tight, going back out. So this is the position of the Y junction box, 2.5 kilometers away. You see this peak at the first fault crossing, a peak of about 30 to 40 microstrains. The little blue dots are data points every 2 meters, and the red curve is a sliding average over 100 meters. So you can see there's a very clear peak here at 2.5 kilometers from the Y junction box. And there's also a peak here at the third fault crossing, which is 4.3 kilometers from the observatory. And what's interesting as well is that we see the signal in both the tight fibers as well as the loose fiber. These are now the seafloor geodetic stations, which we installed a network of 8 such stations on the seafloor. They're acoustic beacons here in the pink cylinder on a tripod, and they send pings to each other. They go beep, 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 and they talk to each other. And the time of the recording of that acoustic signal, that's what's recorded. There's also an inclinometer recording the inclination. There's a pressure sensor. There's a temperature sensor, and we also measure the salinity, and that's to determine the acoustic velocity in water, which we need to determine the length of the baselines. And now you see in the lower right the configuration of those 8 seafloor geodetic stations with respect to the cable path in orange and the fault trace over here. And so we have 4 stations on one side of the fault and 4 stations on the other side of the fault. And if there's no movement, then all of the baselines should stay rigorously constant and not change. If the fault moves as a dextral strike slip fault, as we expect it to move, then the stations 1, 3, 5, and 7, their baselines should remain constant, as should 2, 4, 6, and 8. But then the baselines between, say, station 1 and station 4, that one should get longer. And then the one between 7 and 4 should get shorter. And so that has been down there since October. We recovered the first data in August, late August of this year. It was Jean Voyer who was responsible for that portion of the work. Unfortunately, we were not able to download all of the data. We got about 30 to 40% of the data. And so that's still being processed to see if we can confirm the elongation that we're observing with the fiber optic cable. What I did not insist on, but I will maybe briefly go back and say, I can just say it now, is that elongation of 30 to 40 microstrains over the distance that it is recorded on would correspond to an elongation of about 1 centimeter, okay? And we're hoping that that 1 centimeter of movement can be recorded by the geodetic stations on the seafloor, but we don't have those results yet. So, oops. I'm gonna undo that. So the conclusions, based on our preliminary results, it appears that BOTDR can detect 1 centimeters of displacement at the seafloor, in particular elongation. The shortening is not clearly visible right now. And shortening is also less easy to capture, and our orientation crossing the fault is less favorable to record the shortening. So elongation is best observed on the tight fibers with a signal of about 40 to 50 microstrain, but it's also observed on the loose fiber. And the third point is that our cable is not well buried over large portions of its path length, over probably more than half of the path length. And yet we do observe deformation at the seafloor despite this rather poor coupling. And this is very interesting because that's the kind of configuration we have for telecom cables, which are just draped on the seafloor and are not buried, except up on the shallow platform to protect them from fishing activities. So I will stop there and open the floor for any questions which you may have. Thank you.
Thank you for the interesting presentation, Professor Marc-Andre here. So we still have around 6 minutes to collect the questions. For the participants, we already in the room 5. If you have any question, you can raise your hand. I will notice you and let you to activate or turn on your microphone. Or if you want, also type your question on the chat room. You can leave your question in the chat room. Okay. Maybe I will collect 3 questions. Okay, Mr. Haikal. Okay, please go ahead. Your question to Professor Marc-Andre Gustir.
Thank you very much, Bu Agustina. I also say thank you. Thank you very much for Prof. Mark for the very nice explanation of the recently work on the faults that extends to the offshore. A question for the faults because it's a strike slip faults. Then all the cable that we saw is just crossing about 4 sections of those fault being crossed by the cable lines. So is it if only if the faults being activated by a major earthquake, then does the cable broken will be relay the signal to the sensor, or we cannot got the signal?
Okay, we do not anticipate, shall we say, metric movement of the fault. If we were to have, well, let's imagine you had a magnitude, I think you need about an 8 to make a 1 meter movement on the fault. First of all, we don't anticipate up to a meter or more of movement. But it turns out that the cable, I have some right here in my hand, it's very robust. It can withstand 500 kilos of weight without getting damaged. And then above that, it will start to get damaged. And at 1 ton, it will rupture. So plus the cable is not very strongly anchored on the seafloor. It's in the soft mud. And so it's the accumulated shear stress between the mud and the cable, which is exerting the force. So even if there were to be a meter of movement, that meter would be distributed probably over 300-400 meters, which means the strain per will be pretty low, and that would be within the mechanical strength of the cable, and it would not yield. So yeah, we don't think that the cable will break, barring, well, not from natural causes, let's put it that way. But of course, if a fishing vessel were to trawl on the deep sea floor, which is they're not supposed to do anyway, that could eventually break the cable.
Yeah, it's very interesting because, as you said at the conclusion, it is a communication cables, and all around Indonesia we are a archipelago, so we have a lot of marine cables being installed in our water. So it's very important also to see an update of what your team and your group has been done in this particular area. Yeah, I think it's very important to share this information for us. Thank you, Prof. Mark.
Okay, thank you, Professor Mark Andre, for Professor Distri for the response, and thank you for the question, Mr. Haikal. Any questions? We still have a couple minutes to question and answer session. Okay, maybe 1 or 2 questions. Okay. For me, can I ask you one question, Professor Bircher? Because this topic is very new for me, because I'm not working on this topic. So as you told us before, you use 5 cables. 3 are tightly cables, right, and 2 are loose cable, right? Am I wrong? You put 5 cables in the optic. No, you put 5 cables on the ROV machines, right? The tight cables and loose cables.
Okay, I'm not sure I understood the question.
No,
there are 5 optical fibers in this cable.
Yeah, 5 optical fibers. Yeah, you use 5 optical fibers. And my questions, I'm wondering, I'm curious why you have why some fibers are tight and why others are loose fibers.
Okay.
Yeah,
it's a very good question. It's very important too for the measurements. In general, the telecom industry prefers working with loose fibers, and they're always in the protected core, and then there's gel around them, and and multiple layers of armoring, usually steel wires to protect the telecom fibers in the middle. Yeah, the telecom industry wants because it's an expensive infrastructure, and they want to protect those fibers as much as possible. And so if they're loosely bound, then if there is a disturbance to the cable, then the fibers will feel it less, and they will be less subject to strain. And so the chances of the fibers breaking is also less. So typically the telecom industry prefers loose fibers. In this particular experiment, we wanted to have both loose and tight fibers, because the tight fibers, they are bound by epoxy to the core. And so if something happens to the cable, then the tight fibers will feel it more. And because I was trying to test a strain cable, I wanted the fibers to respond more, for the response of the fibers to be greater. But that means that the fibers are more fragile, they're more delicate, they're more vulnerable. There, that's the word. So it's a trade-off. Tight means it's more sensitive to strain, and therefore it's more vulnerable. And that's what the telecom industry does not want. They want loose fibers, which are as invulnerable as possible.
Okay, I got it. Thank you very much.
I have one more question. Is it okay?
For very brief question, Ms. Haikal, because you have the time is for the presenters.
Yeah.
Session.
What about the sampling rate, Professor Mark? What about the sampling rate? Does these devices could detect the micro earthquake located in those regions, in those soil?
Okay. The technique we're using, the BOTDR, is not very fast. If you want to use fiber optic cables as a seismometer, as thousands of seismometers, then it's the DAS technique, the distributed acoustic sensing technique. And that uses the Raleigh peak, the one in the middle that I was talking about.
Yeah,
and that exists, and that's being used, and there's lots of papers out there. The Stanford and Caltech groups, Anthony Sladen in Nice. There are many, Biondi, Lindsay, a whole bunch of people do that. And that it has a very fast response. Our measurement times are from about 10 minutes to 2 hours. And currently we are making one measurement every 2 hours, because we're sending millions of laser pulses down the fiber and then averaging over that 2-hour period to try to reduce the noise. And so this is for a long-term strain measurement. It could potentially measure slow slip earthquakes, but it will not give you a seismic response in 3 seconds. Yeah, I hope that was clear.
Yeah, understood. Thank you, Prof. Mark.
Thank you so much for the questions from Mr. Haikal Haridi, and thank you for the response and great interesting presentation from Professor Mark Andre Gutstier. We are now moving to the next session, presentations by participants, and we would be pleased if Professor Mark Andre Gutstier is staying with us here in the room. But
I will have to leave and go to work, actually. I'm sorry. I was doing this from home, and but thank you for having me, and
Thank you.
I wish you a good rest of the conference.
Thank you so much.
Thank you so much, Professor Mark.
For the next event or time. Thank you, Professor Mark Andre Gutstier. So now I would like to explain a brief role of our oral presentation. So for each presenters, we'll have 10 minutes to present, and then if we still have time, so we'll collect 1 or 2 questions for the presenters. And we will strictly remind you if the time is coming to over. So I just collect only 5 materials, PPTs. So for the presenters that doesn't have send us the PPT, I would like to ask you to share your PPT by yourself. Okay. For the first presenter, I would like to call Mr. Haikal Haridi to present your topic, about body wave dispersion characteristic. Okay, 10 minutes is yours, Professor Haikal.
Okay, thank you very much, Ibu Sri Agustina. Okay, I will try to share my screen. It's about the relative delay. Okay, can you see my slide?
It's working.
Okay, wait. Now do you see the slide?
Uh, yeah, the slide is about relative delays on body wave.
Relative delay, yeah.
Yeah.
This is correct one. Yeah. Thank you very much. Good afternoon, everyone. Thank you very much for being participate in this ICMR and in conjunction with Unsyiah. My name is Haikal Azifaridi. I will present about the relative delay of body wave arrival of regional deep earthquake between two subduction zones system, Sumatra and Southern Ryukyu. This is a work collaboration between the fkp, TDMRC, PRKP, IES, Institute of Earth Science in Academia Sinica, Taiwan, BMKG, Geophysical, Meteorological, Climatological Institute in Indonesia, and then University Syekh Kuala. Okay, the Sumatra subduction zone. This is a figure of the Sumatra subduction zone. We are living at the northern corner of this big Sumatra island. Here we have the Indian Oceanic Plate being subducted under the Eurasian plate with the motion different from the north to the south. Then we have a number of large mega earthquake occurs along this 4-arc region. So we call this part is the 4-arc region. And then we have the all available stations by the BMKG or the Badan Klimatologi Geofisika Indonesia, shown in this black triangle. Then I want to show to you that in the central part, so we discuss about the Sumatra first. In the central part of the Sumatra, here shown rotated in the right-hand side, where we have the 4-arc island, we have the Simelu, we have the Nias, we have Batu Island, and then we have a 4-arc station indicated by the green colored line here. And then on the island itself, we have this back arc station, which is shown by the red colored LASI, TSI, PSI, SBSI. So if we take a cross section in the middle of this figure, rotated figure, then we can see the distribution of the seismicity from the shallow portion of the subduction zone until to the deep part along the subductions. So we saw the small, big, and small size correspond to the large or small earthquake, and we notice that in the shallow portion we have a big to large mega earthquake occurred, and then we only have a moderate earthquake occurs at the deeper portion at around 100 to 200 kilometer depth. And then we have the shallow part here related to the volcano activity, and then the Sumatra fault zone in the central part of Sumatra. Then we now goes to the southern Ryukyu subduction zone, where it's located in the northern Taiwan. This is Taiwan, located here, and then Taiwan is a very unique, have a very unique tectonic feature where we have two subduction zones. One is from the Manila subduction zone, and one is from the Ryukyu subduction zone. And Taiwan, in conjunction with these two subduction zone region. So in the right-hand side, we can see the close-up figure of this northern part of Taiwan. Then we see a number of the stations. This we call the Formosa array, indicated by the black triangle. This is the data that we use for this study, while the blue rectangles indicate the BATS, broadband seismometer in Taiwan. Yeah, so this is the BAT stations, but the one that we use is the black triangles. And then the subduction trench is located here, and then it's already collided with the Taiwan Island. And then this mark here indicate for the subduction interface. So you go to the deeper part of the subduction zone. Then we saw the record of the body wave record, regional body wave, the deep regional body wave at the Sumatra. If we see here from the GSI, we have the three components, the vertical components, the two horizontal components. Here I already rotate the component to the radial and transverse components in the same way, but for the left-hand side is the GSI, the 4 arc stations, and the right-hand side is the back arc station. So we can observe the signal, which shown a different type of signal. One have kind of a dispersed P wave arrival as well as the S wave arrival, and then in the left hand side also we can see a more frequency content. The amplitude is also larger on the left hand side despite their distance shown here at 200 and 226 kilometers, 22 kilometers. So it's almost the same distance, but we have a different kind of a signal. And this is the 4 arc station, again showing the signal. So the GSI correspond to these stations, and the events is located at 196 kilometer depth. So it's about this one. So the event is here, and then the signal being recorded by the GSI, and the other one, this event is here, the same event, and then recorded by the PSI. So we can see a very different two signal from the 4 arc and the back arc stations. Now the illustration for this interpretation that we saw from the observation, the deep earthquake occurs at this location below the volcanic arc, and then it's for the 4 arc station, it travel within the oceanic crust. So it's being kept as the high quality material, but compared to the oceanic mantle and the continental mantle, this part is having the low velocity compared to the sandwich part in the upper and the bottom. So it can travel within the oceanic crust and then record by the 4 arc island. While at the back arc station, the signal goes directly, penetrate the mantle, continental crust, and then arrive to the stations. So it heavily attenuates the signal, and then only low frequency survive in this type of events. Then we saw this the signal at the 4 arc station have a delay compared to the signal that recorded at the back arc. So at the 4 arc, we can have a delay up until a couple of seconds, depend on the depth of the events. Here I sorted the signal through the depths. So we started from 100 kilometer depth until close to 230. This is a model of AK-135 velocity model. We see the delay of this signal throughout the depths. And then if we stack them all together, we also observe a different first motion of the P wave correspond to the depths. Then for the southern Ryukyu is almost the same. So we find the delay of this dispersed signal, the same thing, there's vertical component and 2 horizontal component at the station that sample the subduction slab. This one doesn't sample the subducting slab. We see the immediate impulse signal for the non-sample, but for the one that sample the slab, the impulse is being delayed a couple milliseconds or couple seconds before after the first arrival. The same thing here, we can see a very clear non-impulse signal on the P onset. We have the impulse arrive afterwards, while the one that non-sample the subducting slab, immediate impulse being observed. Then this location of the stations, if we see here, all the way down, this is the stack record section of the seismogram. On the left-hand side is the distance of the station correspond to the event on the red color. And then we see that the station WU18 is having the late arrival. Yeah, it's located here, close to the subducting front. And then as well as the other station for the WU10, beside of the first station that I shown, this also indicate a delay. So this is for the conclusions, for the illustration of those observation. We find that if the events located on the oceanic crust, the wave, the ray will travel and trap within this low velocity layer of oceanic crust, and then detect by the 4 island stations, such as at the Sumatra and at the Southern Ryukyu. But we do find Southern Ryukyu have a larger delay compared to the Sumatra. So it's probably the oceanic crust at the Southern Ryukyu is more thick rather than at the Sumatra, or we have another such as underplating or some other phenomena, tectonics expressions along the subduction zone at Southern Ryukyu. Okay, that's all for my presentation. Thank you very much.
Thank you, Dr. Haikal, for your presentation about the relative delays of the delay process. But however, 10 minutes is over. So excuse us, we can't allow you to get the question from another participants. But however, if anyone has questions for Dr. Haikal, you can leave your question in the chat room. And I will allow all the participants in room 5 to communicate each other in the chat room. So please don't hesitate to use the chat room to communicate or discuss your topic. Okay, we will move to the next presenter, Mr. Nguyen Phu Dung from the University of Transport Technology, Vietnam. Dr. Nguyen Phu Dung will present about impacts of climate change on coastal provinces and cities of Vietnam, reality and emerging problems. Dr. Nguyen Phu Dung. Okay, I guess she or he is not here yet. Or okay, we will go to the next presenters. Dr. Riza Yuliratmo Setiawan will present about satellite remote sensing reveals coastal wind variability of the Central Maluku Island. So 10 minutes is yours. Please, Dr. Riza Yuliratmo Setiawan.
Thank you very much, Ibu Agustina, for the opportunity and also for your kind help this morning. Yes, ladies and gentlemen, please allow me to introduce myself. My name is Riza Yuliratno Setiawan. I am a faculty member of the Department of Fisheries, Faculty of Agriculture, UGM. Today I'm going to talk about our preliminary results on the observation, on the satellite observation of the Central Maluku Islands. Why we are interested in investigating this region? Because to our knowledge, this region is purely studied in terms of sea surface variability. And the most importantly is that this region is located in the main part of the Indonesian through flow, or ITF. As you know, 80% of the ITF water mass passing through the Sulawesi Sea and Makassar Strait, and the rest of the water mass are passing through the Maluku Sea and then going through the Limatola Passage, and the other passage is the Halmahera Sea, and there all of these water mass are mixed in the Banda Sea. Yes, this is our motivation why we are working on this region. If we look at the bathymetry map, this is bathymetry map of the region of the interest. Our studied area is characterized by complex bathymetry. So the dark blue color represent the deeper oceans, while the red color represents the shallow waters. In the study, we mainly analyze satellite data because we don't have access, or this region is purely observed by in situ measurement. So we mainly employ the ASCAD wind data. This data has a spatial resolution of 20.5 kilometers, and we analyze daily data from 2007 to 2019. Similarly, we also analyze the SST data and chlorophyll data derived from the MODIS satellites. This data has similar resolution, that is 4 kilometer, and we use also the daily data from during the period of 2007 and 2019. Then we further analyze our data by correlating all of the data with the ONI. This is index for the El Nino or ENSO events, El Nino and La Nina. And we also correlate our data with the dipole mode index. This is the index for the Indian Ocean dipole. Then all of the data used here were computed into monthly and monthly climatology. This is our results. This figure shows the wind stress during the period of December to February, and as you can see here, the region of interest here is characterized by relatively weak wind stress, ranging from 2 to around 5 Newton per meter square meter. And then on the other hand, from July to September, the region of interest is characterized by strong wind stress, especially from July to August. Here we can see here the strong wind blows in this region, and our analysis suggests that there is a strong enhancement in the corner of these Buru Islands. Probably this is due to the effect of orography or high coastal mountains in here. So this is the topography map. The brownish color represent the higher topography. And we also observe that strong wind stress also appear in the small straits in these regions. Okay, and this is the results of the SST analysis from December to February. And this is the results of the analysis. This is the SST analysis of July September period. So you can see here there is a distinct characteristic of SST in the region, especially from July to September. The central Maluku Islands are characterized by a very low SST, reaching around 26 degrees Celsius, while from December to February, the islands or the region of interest are characterized by relatively warmer SST. Next, we also analyze the sea surface chlorophyll in the region. So from December to February, the region of interest is characterized by oligotrophic condition. That means the productivity is low in here during this period. In contrast, during the period of July-September, the studied area is characterized by relatively higher chlorophyll A. So this observation suggests that there is a strong primary productivity in the surface ocean during this period, from July to September. Yeah, we further analyze the data by correlating all of the ocean parameters with the ONI and the MI index. So the red one is the MI index, the black curve here represent the ONI index. So this is the result of the correlation between ONI and surface wind. We can see here there is a positive correlation between these two parameters. The red colors represent positive correlation, whereas the blue color represents negative correlation. Similar result also observed in the correlation between DMI and surface wind. Even in September here, we observe very strong correlation between DMI and surface wind. So this is the result of correlation between ONI and SST, sea surface temperature. There is a negative correlation between ONI and SST. So here, during the period of July to September, the region of interest is characterized by negative correlation. Similarly, the correlation between the MI and SST suggests the similar result, that is negative correlation. Interestingly, correlation between ONI and surface chlorophyll A shows positive correlation, especially in the regions in here. So very narrow region in here is characterized by positive correlation. And then we also can see here the correlation between TMI and surface chlorophyll A also suggests positive correlations. So to sum up, our preliminary research here show that the importance of coastal wind and extreme climate events. In this context, we use ENSO and IOD as indicator of extreme climate events in shaping ocean condition and perhaps regional fisheries production. That's all my presentation. Thank you.
Okay, thank you for your presentation, Dr. Riza Juliratna Setiawan. We still have 1 minute more, so I will collect one question maybe if any of you have question for Dr. Riza Juliratna Setiawan. Okay, please raise your hand if you have question. Okay, I think that's very clear presentations. No have questions. Okay, thank you once more. Thank you very much, Dr. Riza Juliratna Setiawan. So we are going to the next presenter, Dr. Muhammad Shukri. Dr. Muhammad Shukri.
Can you see that the
Dr. Muhammad Shukri have the presentation about seismic velocity correlation, seismic velocity correlation generated from refraction and downfall measurements. Okay, I'm going to check Muhammad Shukri. Okay, he is not here. Okay, so the next presenters after Muhammad Shukri is Dr. Jamila Husna. Dr. Jamila Husna has the presentation about the differences of the atomic and the optical properties percentage of ZNO material that caused by variance annealing temperature treatment. Dr. Jamila Husna or Miss Jamila Husna? Okay, I can't find the name of Dr. Jamila Husna in the list of participants. So the next presenters is Professor Syed Y. Krimpli from the L.N. Gumilia of Eurasian National University. We are talking about estimation of the volume of production of turbine vapors of a fuel boiler with stochastic exogenous factors. Professor Syed Karim, please. Okay, I also can find the name of Professor Syed Karim in the list of participants. So the next one, number 7. Number 7 is Dr. Sabrina Hasibuan. Okay, Sabrina Hasibuan is here, right? Dr. Sabrina Hasibuan?
Yes, I'm
Okay.
here.
Oh, very good. Okay,
Okay.
so this time is yours. So you will talk about the sedimentation rate of feed on the ground pond, red, yellow, pozolik, patin intensive fish farming. Okay, you have 10 minutes to present and the time is yours.
Okay,
So,
I'm Sarah.
yep.
I'm Sarah, my PPT. Okay, thank you, Ibu Sri Agustina. Can you see my slide?
It's starting, so I think it's take a few seconds.
Okay, everyone. I'm sorry, my video off, so I can see my face to all of you. Is it not problem?
Yes, it's working now. So
Okay.
your PPT is
Okay.
on share sharing.
Okay.
On share
Okay. My research in sedimentation rate of feed on the ground pond, red yellow pozolik, we call PMP, in patin intensive fish farming. I researched with Pak Gita Sastria. Pak Gita Sastria make a model, the sedimentation. The red yellow pozolik is it USDA identification is multi-solpon, rich soil element Al and Fe. The secondary mineral content dominated by the type 1 intensity and effective by weathering process and intensive use the pond and the pond age. Advantage is the ability of soil PMG, excellent in farming flocculants. So we can see the water is increased water clarity. The material of settle out the pond to the sediment can be divided to source. One particle on organic material biogenic on gravity greater than water such as algae dye, excretion of fish and feed residues, and suspended materials that go with the flowing water and continuously settle in the bottom of the pond. This sedimentation process has a significant impact of the balance of the material contained in the pond. The second source, resuspension of particle from the bottom of the pond. Resuspension of the material is a common mechanism of the transportation of the nutrient from the sediment to the water column. The used sediment trap can be more effective to help measure both of the source of a particle that occur in the pond. However, the rate of sedimentation pond of stock in the patin rate intensively and need to the assessment so that productivity can be maintained on. Method. This study measured the rate sedimentation in patin pond intensive fish farming below the method recommended Munsiri et al. 1995. But now we can use the method, it is relevant. Field-scale research conducted to the Center of Protein Fish Farming in the village of Kota Masjid Kampar. This study used complete the randomized design, which used the one factor is of the egg for the level of the treatment intensive of patin aquaculture pond and the 3 replication. P1 is it a pond intensive of patin aquaculture age 0 to 5 years, P2 6 to 10 years, P3 11 to 15 years, and P4 age 16 to 20 years. We can see the pond different, even the age. This is a schematic of pond soil profile, Munsiri et al. 1995. We have two phase, solid phase. This is soil pond bottom pond, like it ultisol, and the up is a column water column. So we put it use of the sediment trap, 10 centimeter from the bottom soil, and the up 10 centimeter from the surface water. Sediment trap can collect the particle size from the water and from the soil. We average the sampler. That is we can see a pond with a different age. Yes, and the result we can have a data because we put the data every week. So we concern to total solid, the page of 0 to 5 years, 10 to 6 to 10 years, and 11 to 15 years, and 16 to 20 years. The format we look the pond egg 6 to 10 years different with the another line. So we see the data increase, then the stable. The another graphic is show the data increase. Yes, the increase. So the sedimentation, we can conclusion is based off the distribution of data, the sedimentation for pond age 6 to 10 years use the linear regression method with the polynomial model based on the order 3 obtain similarities to the red chain of the sedimentation is what's called is the equation. Yes, the average rate the sedimentation is based on the equation is 90.3431 milligram per liter per weeks, or 12.909 milligram per liter. Thank you very much.
Okay, thank you very much for your presentation, Dr. Sabrina Hasibuan. Could you stop your share screen? Yeah.
Yes.
Yeah. Could you stop your share screen? Okay. Okay. So, any question? We still have some more time, some more minutes to collect a question and answer. So, questions about the sedimentation rate, right, Mr. Sabrina? Sedimentation rate.
Yes, yes.
Yeah, okay.
I'm sorry, I'm a problem with the presentation. We can out the share.
Oh, okay, no problem. So, let me see. So you can. Okay. You you can click at the top on your computer screen, and then you can click the stop share there.
Yes, I can find at the stop share.
Okay.
Oh my God. Sorry. I try.
Okay, my friend maybe can help you. Can help you to stop the sharing. Okay.
I,
No. Okay.
where is it? Okay, stop share. Thank
Okay.
you.
Okay,
Yes.
thank you. Okay. Any question for Dr. Sabrina Hasibuan?
Yes.
Any question? So I think this is also clear presentations. Thank you very much for your presentation, Dr. Sabrina Hasibuan. Okay,
Yes.
thank you so much.
Okay.
So we will go to the next presenters. Mr. Koko Ondara from Marine Science, Universitas Kuala, and we'll talk about concentration of dissolved heavy metal around the Rupat Waters Industrial Activity, Malacca Strait. Mr. Koko Ondara?
Yes, I am.
Okay. Okay. Do you want me to help you share the screen, or you will do the share screen by yourself?
Sorry, maybe I asked to the moderators to show my PPT, please. I'm currently having outside activities. So I will presenting with my phone, so I get difficult with PPT with my phone. Sorry.
Oh, I see. So this is your PPT, and 10 minutes is yours.
Oke, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Good afternoon. Thank you for the time, Mrs. Sri Agustina as the moderator, and I see Mr. Haikal, all the presenter and participant. It's really a wonderful time to be here attending Invice conference to be with all presenter. So I'm Koko Ondara from MMEF, and I'm writing this paper with my partner Ruzana Diauddin, Ulung Jantamawisa, also from Ministry of Marine Affairs and Fisheries, and my friend too in Syekh Kuala University, Sahrul Purnawan. I will present our results with the title Concentration of Dissolved Heavy Metal around the Rupat Waters Industrial Activity on Malacca Strait. Next. Okay, this is our research has been looking at. So like that started. Sorry, next. This is for introduction. Based on the title of this paper, there are two questions. Why heavy metals and why is it located in the Rupat Strait? As we know, heavy metals are useful and needed by the body, but in certain concentration. But if it exceeds too much, the predetermined limit, it will become toxic and dangerous for the health of living things. Heavy metals that have density exceed more than 5, which is classified as a pollutant, and are dangerous because they will accumulate in the water column, sediment, organism, and cannot be degraded naturally. So why Rupat Strait? Rupat Strait is the waters, the strait is located between Sumatra Island and Rupat Island. The strait is semi-enclosed water, which makes the oceanographic condition of this water very dynamic. Dynamic external factor that influence it. The Rupat Strait is one of the water transportation route that were widely used by the ship. Okay, next. This is a material and method. There are 5 heavy metals on waters to be analyzed. That is cadmium, copper, lead, zinc, and nickel. the value of heavy metal content in the waters will be tested for the suitability of water for marine biota based on the Minister of Environment Decree number 51 of years 2004. So this is research was carried out for 3 days, August 28 until 30, 2020, which was carried out at 9 observation stations. Water samples taken while the surface, it means less than 1 meter deep. The water sample was bring to the laboratory and to determine the value of heavy metal contents. So this is the 9 location in Rupa Strait. We know this is industrial activity and unique sediment, unique oceanographic condition, and unique located. So the objective is health sustainability of marine waters. Next. This is the result. The first heavy metal is the cadmium. The cadmium in the waters of Rupa Strait, it is range from 10 to the -4 to 21 to the -3 milligram per liter. The cadmium value at the observation number 1, 3, and 4 didn't meet the marine water quality standard that had been set at 10 to the -3 milligram per liter. Cadmium value for observation station number 2, 5, 6, 7, 8, and 9 are below 10 to the -4, and meet the this value, it meet the water quality standard for the marine biota. Next. And the second heavy metal is coprum. The threshold value for the coprum concentration is 8 to the -3 milligram per liter. The coprum value in the Rupa Strait is 0.11 milligram per liter to the 0.38 milligram per liter. So it exceeds the threshold that has been set for the all observation point. We can see the figure. All the value is doesn't meet the system the suitability. So the state show that the Rupa Strait receives sufficiently high coprum that is contain pollutant. Next. And the next heavy metal is the lead. It's symbolized by PB. The lead value in the of Rupa Strait is below 10 to the -4 milligram per liter. And all of this value is still below the water quality standard for marine biota. The standard is 8 to the -4 milligram per liter. So this result show that there are no contamination of lead within the Rupa Strait, or perhaps device used in the laboratory couldn't detect the concentration of PB, which the concentration of lead might be tremendously low. So PB is kind of heavy metal that relate to the human health because it could impact on the large number of kind toxicities, environmental pollution, and harmful toxic properties. Next. Sorry, next. Okay. And the next heavy metal is the zinc. So we can see from the picture the zinc concentration in the waters of Rupa is ranged from 0.24 to 0.43 milligram per liter. This value exceeds the maximum limit of marine water quality standard. The marine water quality standard is 0.05 milligram per liter. The high concentration of zinc It could be sourced from the presence of pier, shipping lane, and shipbuilding activity within the Rupa Strait. So this metal can treat the survival of local marine biota. So I think metal distribution in the water environment depends on biochemical alteration in the water and surface. So as we see, the zinc doesn't. Next. Okay, it's the nickel. This is the main source from industrial and household waste. And the maximum threshold is 0.05 milligram per liter. And as we see, all the value of the nickel is still below the maximum water quality standard at 0.05 milligram per liter. And there is no contamination of nickels. Next. So this is the conclusion. As we see, the nickel still meet the threshold value set by the Minister of Environment Decree number 51. As many as 30% of the sample location for cadmium do not meet the quality standard and have been polluted. But there is meanwhile the value of copper and zinc have exceeded the specified quality standard and have polluted the waters of the Rupa Strait. So this is 5 parameters, and the result: 2 pollute, 2 not pollute, and 1 70 not pollute, 30% pollute. So that was the presentation of the result, our research that have been done. So next, I please to the moderator. Thank you.
Okay, thank you for your presentation, Mr. Koko Ondara. We still have 1 minute, maybe any presenters, any participant have question about heavy metals and Rupa Strait. Okay. Question? Okay, no question. So that means it's very clear presentation. Thank you once again, Mr. Koko Ondara, for your presentations. So next, we are having Dr. Winnie Ratna Melani. Dr. Winnie Ratna Melani will present about characterization of hydrological aspects in Kolong 6 Pond, Kijang, Bintan Island, Indonesia. Okay, so you have share your PPT by yourself. So you have 10 minutes to present. The time is yours.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you, moderator, for the opportunity time for me. Good afternoon, ladies and gentlemen. Is today a wonderful symposium in Zoom meeting here. Okay. Let me introduce myself. My name is Winnie Ratna Melani. This is an honor for me to presentation our study with characterization of hydrological aspect in Kolong 6 retention basin, Kijang City, Bintan Island. The study was conducted by research team from the Department Aquatic Resources Management, Faculty of Marine Science and Fisheries, Universitas Maritim Raja Ali Haji. For my partner in my research is consisting Mr. Andi Zulfikar, Mr. Tri Apriyadi, Mr. Wahyu Muzamil, and then Mrs. Deni Sabriati. Okay, for you all to know, The research is an introduction research, so on overview characterization of hydrological aspect in Kolong 6 retention basin. And then as you know, my Bintan Island is a small island. And then we have very limited water catchment capacity and have a specific hydrological condition. Is Kijang City in early year 2000. This sector was no longer a priority due to the diminishing economic potential of granite and bauxite resources. And abundant bauxite mining pits on Bintan Island has a change, yeah, and the land cover pattern on a lot of and all left the post mining piling pond, which is known by the local community is Kolong. That's Kolong is namely local. Okay. And then Kolong 6 retention basin is not dam, lake, or river. So it is necessary to know the characteristic and catchment area as well as vegetation aspect to determine rainwater retention. And then need to know to Kolong 6 retention basin in Bintan Island is expected to have dynamic hydrological characteristic of the existing reservoir or water reservoir. Sorry. And our using to method this research. Our using package of CAN 2021 and program R core team 2021. And then the flow analyze, yeah, you all can see my flow analyze this slide. The flow analyze is a random forest classification method used for each image Landsat 7 and Center 2. And we see the flow analyze. In the first stage, satellite imagery must be available to get the final map because the research we have a final map, yeah, into the first time. Next, data collection. We must have data collection, image pre-processing consisting of geometric, rendrometric, pan-sharpening, and land masking. And furthermore, it was also equipped with field reference data. After the data is collected, the next step is pixel value extraction. And divide this the two data set, namely training data set and test data set. Based on data statistical and accuracy assessment, visual examination. And finally, we got a final map. Okay, the result for my research and geomorphology of watershed Bintan landscape based on digital elevation model, data processing. Information obtained from data on the island of Bintan has 9 sub watershed with character slope average, rather steep terrain, elevation average 11 to 16 meters. And then my result, geomorphology of watershed, kolom 6, retention basin. Kolom 6 retention basin is one of the raw water sources in this study, is located in Kalang Tua watershed. Catchment area for kolom 6 basin retention 1067.31 hectare. Based on result of the morphological analysis present, could you see in the map image above? Kolom 6 retention basin is one the water and basin retention 1067.31 hectare. In the next image found, kolom 6 retention basin slope average rather steep trend, elevation average 20 centimeter, and categories the highest river order 3. Now, the highest river order 3 is know that the kolom 6 retention basin hold water from a high hill area in Bintan Island, especially in Gunung Lengkuas area. The geographical condition of the sub watershed so that the kolom 6 retention basin catchment area consists of 3 river order. The sub watershed name is Kalang Tua and the catchment area is kolom 6 retention basin. The location of the retention basin that catch water from steep to flat area will determine the availability of raw water to meet of water need by society, especially in the dry season, with a catchment area of 1067.31 hectare. The result of the morphometric analysis present in map image so that the steep upstream slope and the flat downstream slope have green potential to fill water reservoirs during the rainy season. And and then my result about vegetation coverage. You can see this slide. Based on random vegetation method, vegetation coverage in kolom 6 basin retention, analysis of vegetation coverage result in kolom 6 retention basin area from year 2000 to year 2019. To year 2018. Indicate decrease in vegetation coverage in the water catchment area. There is a decrease in the area of 326 90.47 hectare. Based on condition of the vegetation coverage in year 2000, the vegetation coverage of forest land was still dominant, indicated by vegetation coverage that classified as dense. Based on vegetation coverage condition in year 2018, it could be concluded that vegetation coverage is still dense only in the upstream area, but has begun to turn into open land in the catchment area around the retention basin. And then we can see this slide. The vegetation area decreased year by the year for 18 years. Acute due to the cooperation of various land to other land uses, so that it implication for quality and area of the forest decrease. If this condition is not controlled, it will affect the water catchment capacity of the Kolong 6 retention beach. It's maybe a situation is a critical situation based on vegetation.
Pardon, excuse us, Dr. Winnie, can you go faster because your
Okay,
time is over? Yeah.
Yep, it's the last my conclusion. This my research. Well, based on study, the conclusion obtained are as follow. And one, Bintan has a 9 sub-water sheet, and Bintan Island generally has a rather steep terrain with 11 more than 25. The catchment area of Kolong 6 retention basin has an area 3 river order, and then this is my conclusion. Thank you, moderator. That's all my presentation. Thank you.
Okay, thank you, Dr. Winnie Ratnamelani. Since your time is over, so I can't give you opportunity to collect questions. So, but for anyone who has question for Dr. Winnie Ratnamelani, you can leave your question on the chat room. Okay, next we have presenters, Professor Syed Karim Kulay. Okay, Professor Syed, are you here?
Good day, dear participants of the International Conference and the National Symposium.
Yeah. So I have your presentation. Would you like to share by yourself, or maybe you need you want us to share your PPT? So which one is your prefer? Okay, good. Okay, you have 10 minutes to present. Okay, you have 10 minutes to present, and the time is your professor. Please.
Slide. Slide show dengan gaya turun. My name is Sesi Karim Kulay. I am a professor at the Eurasian National University from Nur-Sultan City, Kazakhstan. We present to you attention the results of the scientific research on the topic estimation of the volume of production of turbine valve of a full boiler with stochastic exogenous factors. And so after of this work are Gulmira Aziyeva and Ainur Saliyeva. Also, it's from at the Eurasian National University, Nur-Sultan City, Kazakhstan. Next slide. The purpose and the problem of my presence provide and an analysis, the review of technological solution on the conceptual principles, methodology, and the practice of modeling the steam water processes of the full boiler of power plants. To implementation of algorithms and the models of the theory of system dynamics, white and pink noise. To using computational technologies and difference schema equations and methods of numerical integration to determine the value of the input parameters to product turbine steam of a full boiler, which regardless of stochastic exogenous factors provide stable state of the necessary and the model volume, the rate of water intake, and the output turbine steam of the full boiler. Next slide. Slide number 3 gives a mathematical formulation of the problems of this work. Let boiler at an endogenous indicator of the volume driven steam production boiler for period T. И так далее. See a question with number 1. Under necessary initial volume of turbine system product. See initial condition with number 2. Next slide. Slide number 4 gives a limited condition for steam water process in a full boiler. Formula 3 and 4. Next slide. Slide number 5 gives a conditional and variables for system water process in a full boiler. Let denote adjustment for boiler variables and expected steam rate variables. Next slide. Slide number 6 given conditional and variables for steam water process in a full boiler. Indeed denote steam rate. The norm of turbine variable are assumed to be equal to the volume production of turbine variable of the full boiler in with a constant average production life cycle. Next slide. Next slide. Slide number 7 gives the variable for steam water process in a full boiler where input dimension variable that provides simulation of input, for example, step, pulse, sinusoidal data, and pink noise, random noise data. Next slide. Slide number 8 shows the value of constant for steam water process in the full boiler. See equation with number 10. Also, models will be implemented in any logic to estimate the input parameters value to steam water process. The slide number 9 shows a computer simulation of the first order boiler management model, which allows obtained numerical results to ensure the stability of the steam water process in a full boiler. Next slide. The slide number 10 shows a computer simulation of the first order boiler management model, which allows obtained numerical results of the expected influence of exogenous factor on steam water process in a full boiler to ensure the sustainability of system steam water process in the full boiler. The next slide. Slide 11 shows first order boiler management model, computer simulation, which allows you to visualize and estimate of the volume of production of turbine warp of full boiler with stochastic exogenous factors. Next slide. Conclusion. Based on the analysis and the review of the conceptual principles, methodology, and the practice of modeling water steam process of the full boiler of power plants, implementation of algorithms and models of the theory of system dynamics, white and pink noise, using computational technologies of difference Schema equation and numerical integration methods, the value of the input parameters of the production turbine warp on of the full boiler are determined, which regardless of stochastic exogenous factors provide stable states of necessary and model volume norm and of water intake and in output of turbine warp of the full boiler. Next slide. Slide 30 provides a list literature used, conduct and literature review and review of technology solutions of the conceptual principles, methodology, and the practice of modeling the steam water process of the full boiler of power plants. Next slide. Thank you for your attention.
Thank you very much, Professor Karim Pule, right? Yeah, yeah. I hope I pronounced your name correctly. So, any question for Professor Karim Pule? Maybe one question. But about the production of the.
I need to translate. I need, please. I need to translate. Speak English.
Okay.
Сейчас мне помогает help my assistant.
Если вопросы, Папа. Okay, we are waiting. Any questions from auditors?
Yeah, any questions for Professor Said Prince? I'm sorry, I can't speak Kazakhstan, so I can't help you where you are here. So yeah, you are just as interpreter. Okay, I think that's very clear presentation.
Можно ли перевести там?
Ишинке айтады, Қазақстанда болған жоқпын. Сұрақтар әлі жоқ, күтіп отырмыз сұрақтар. Папа, күткен күте тұрмыз.
В общем, это біз айтсаңшы Қазақстаннан деп Евразийский университет сонда кафедра департмент информационный систем. I work the chair of information system.
Okay, nice to meet you, Professor. Yeah. Okay.
Сұрақ жоқ дей ма? Вопрос нету, да? Кім жауап беріп отқан? Гүлмира ма?
Сейчас, подождите.
Okay, I think we don't have question for Professor Sidkrimpuli. Your presentation is truly clear. So thank you for your presentation. And now we are going to move to the next presenters.
Okay, thank you.
Okay, could you please stop your screen? Could you please stop your sharing screen?
Жоқ, выключайтесь.
Okay.
Хорошо, спасибо.
Thank you so much. So we still have one presenters here, Dr. Andrian C.H. Simanjuntak. Dr. Andrian Simanjuntak. Dr. Andrian Simanjuntak. Dr. Andrian Simanjuntak's topic is swarm earthquake in Kota Chane, Aceh, volcanic or tectonic activities. Okay, I'm going to check in the list of participants. No. Okay. So, Dr. Andrian Simanjuntak is not here, so I think it's all of our presentation in room 5. And thank you so much for your contribution, your cooperation, and your amazing presentation. Please close the line for all of us. Yes.
We can suggest to the participant to join again our main session.
Yep.
Oh, I think Adrian is just signing in.
Oh, Andrian is
just
okay.
signing in. Yeah.
Okay, Mr. Andrian Simanjuntak is here.
Yes.
Okay, so this time is your time to present your topic. Let me check. Do you want to present your topic do you want to share your material by yourself?
Yes. Can I share my screen?
Okay, you have 10 minutes. You have 10 minutes to present, so the time is yours.
Okay, thank you, moderator. I think you can see my screen or your guys.
Yes, your screen is white background and swarm earthquake is there. Right.
Yeah. Okay. So can I start?
Yeah, please.
Okay. Good evening for you, ladies and gentlemen. So in this time, I want to present my recent research about the swamp earthquake in the Kota Chane. So this event is rare and so interesting because no swamps events can found before in Aceh province. So in the last decade, this is the last swamp earthquake in Aceh province. So this is my presentation about swamp earthquakes in Kota Chane, volcanic or tectonic activities. Okay, so this is the figure I make to inform you all guys about the seismicity map in Aceh province in the last decade. You can see if all earthquake in line can be found in the fault zone from northern part, started from Salimum fault up to Renon fault in the southeast Aceh. So the earthquake, the swamp earthquake occurred in September to November 2020. Previously, no swamp earthquake can be found in the Aceh province. You can see in the left picture, there is only big earthquake, no swamp event, because swamp event is usually connected by low magnitude events. So you can see in the right picture, there is I think there's not Gunung Burnitalang, there's Gunung Bendahara or Mount Bendahara. There is a volcanic mount in the northern part of Southeast Aceh. So the swamp activities were clearly located close to the Tripa Fault, but also beneath Mount Bendahara. So we cannot say this is from fault, because it also close to the volcanic. So why I choose the title of this research, volcanic or tectonic, because the swamp event can be connected to the fault activities or volcanic activities. There is 103 events recorded by the nearest station, namely KCSI. So this is so in the seismic waveform, we can see clearly the typically waveform of seismic marked by P wave and S wave. So this is very important. Why? Because this sign or this phase is usually used to locate the earthquake. So when we pick precise the PNS, we can get the ideal location. So this is the graphic between S and V phase, and you can see in the right part there is an earthquake in September to October, but before the swarm no event, and after the swarm no event. So this is the rare event because only occur in only 1 month. In the left part, you can see the graphic is so noise, too many noise. So we need too many errors. So we need to filter again to get the travel time graph, the nice travel time graph. So this is after we filter again. So you can see if the linear solution of the travel time make a relation with low deviation. So the ratio is 1.763, with total peaks are located in the range 15 and 40 second data. So the this arrival time data will be processed by absolute relocation with failures, and then relative relocation to the furthermore analysis with hypo-DD. So this is the result. The result is about, so we focus about to get the model, the good model with the tectonic condition in Southeast Aceh. So we gain 100 initial 1D velocity models with a priori models, and then we did simultaneously inverted to get the solution, the unique solution you can see in the right part. So we can see from the figure if the red line is highly precision, the velocity model will be used to locate again the earthquake, the hypocenter. So you can see if the red lines is converged from the a priori model in the left, and then the right, that all initial model converge to the red lines. So it can be concluded our solution is unique and converge. So we will use the 1D model to further analysis like relocation, and then to decide the mechanism of earthquake. So this is the last recent analysis from us. So you can see if all the earthquake, this is the tectonic system in the Southeast Aceh. So you can see if 20 December and 2020 there is volcanic earthquake, and no, I think that's not volcanic, but this is the fault activity from local fault. So I think our preliminary results indicate that the volcanic activities from Mount Bendahara may trigger some seismic activities in the lower crustal, but while intense activities of swarm in the most upper crustal, maybe from dike or other fault activities. I think that's enough thank you. So I think you guys want give want to give any comments or question?
Okay, please, anyone comment? Yeah, comment for Mr. Andrian or questions about the tectonic or seismic activity or something, yeah, related to the seismic or tectonic, yeah, earthquake.
Andrian, I have one question.
Oh, okay, please, Mr. Hekel.
Is
Yep,
there any, based on the signal that you have, do you see any different signals between the volcanic activities and the tectonic activities? Like if the swarm occurs and at the relate to the volcanic, I'm pretty sure you're gonna see a lot of the micro seismicity with a long period. Do you see those kind of signals?
Okay, that's a very good question. Okay, thank you for the nice question. Okay, so the problem is the nearest station, the close station is KCSI. So there with 100 and 103 events, that's a very clear location. But when we only use single station, we can see many earthquake. For example, in 1 minute or 2 minutes, we can find 3 or 5 events, but only in KCSI. But it is very difficult to locate with single station. So this is the challenge. But in this research, we only focus to get a 1D model by travel times. But in the further analysis, we may include the waveform analysis to see, like Haikal said, there is maybe different typical waveform between fault activities and volcanic activities. There is maybe long period or short period. I think that's a very challenging analysis. So we firstly get the 1D model, and then the 1D model will use maybe for further analysis, like Pak Haikal said, to see the waveform typical to make a different suggestion. There is volcanic or tectonic. I think we need to include waveform analysis. Thank you for the question, Pak Haikal.
Yeah, thank you. Very clear. Thank you.
Okay,
Very
thank
good
you for
job.
the response. Okay, thank you for the response, Mr. Andrian. The time is over. So thank you very much for your presentation. And now
You're
we still have
welcome.
maybe one presenters, one topic by Mr. Haikal. So you still have one title.
I still have one title.
Okay, right. You still have one title, body wave. Okay, time it is yours.
Okay, thank you very much, Ibu Sri Agustina, and yeah, for all the participants, will be the last presenter in this room. Today I will present about the body wave dispersion characteristic of regional deep earthquake at Sumatra and Southern Ryukyu subduction zone. So if you already attend the first talk, I already discussed about the delay time of this body wave. So I'll just repeat it again. We have this Sumatra island located at the southeastern corner of Eurasian, and then we have the subducting trench at the offshore location. We have the Australian oceanic plate subduct. You see the contoured line here indicate for the subducting plate interface. Different color indicate the different depths of the interface. And then this large circle indicate the big earthquake with a large magnitude, followed by a small earthquake correspond to the information here shown here. And the deep regional earthquake that we analyze is located at this portion of the subduction zone. So it's located about 100 to 200 kilometer depths. Then if we focus on this central part of Sumatra, we can see a distribution of the island, of the 4 arc island with the 4 arc stations. And then we also could see the back arc station indicated in the green for the 4 arc and the red one for the back arc. Compared to the southern Ryukyu subduction zone, the Taiwan here, located here, the island of Taiwan, is in conjunction with the Manila subduction zone at the southern part and at the Ryukyu subduction zone on the northern part. And part of Taiwan is created in collusion between these two subduction systems. So they have earthquake all over the Taiwan island. And then we focus on the northern part of Taiwan. We see a lot of the Formosa array station indicated by the black triangle and the BATS seismometer, broadband seismometer indicated by the blue rectangle, the subducting trench, and then the plate interface indicated with the same contour line. For the cartoon illustration that we already shown before in the previous presentation, we indicate that the 4 arc station shown the signal having high frequency content with the large amplitude as well as the dispersion. So the 4 arc located here and the earthquake events located here on the oceanic crust. Then compared to the big arc, we lose this high frequency content, so its low frequency is already attenuated, and then the amplitude is also much smaller despite the distance between the 4 arc and the big arc. The distance is almost the same. Here for the illustration of the real conditions, where we have the earthquake located here, so the wave travel within the oceanic crust and then recorded by the GSI at the 4 arc stations, while for the PSI, it goes penetrate the continental mantle and then arrive at the PSI at the northern part, at the back arc stations. And then seeing from the spectral domain of the signal, now we can see very clearly that the 4 arc station indicate the dispersed body wave. Here I show only for the P wave. So the energy of each frequency indicate in the spectrogram. So the bottom panel is the spectrogram and the top panel is the waveform. The frequency of each energy in each frequency arrive different, having a delay time compared to the first arrival. So a dispersed signals indicate low frequency arrive first, and then the higher frequency arrive later. We can see a delay of high frequency. While the non-dispersed signal, the high frequency arrive earlier, and then the low frequency arrive later. So this one did not sample the slab. This one sample the slab and the oceanic crust. Okay, so based on that, we can observe the dependent arrival relate to the low frequency signal. So we can have the dominant frequency for each station, and then we can observe in which frequency and how much delay that they being received for the stations. So for the Sumatra, it's about 2%, 2 until 4% of delay. We check here is about 2 until 4% of delay of the P wave and the S wave. And then for the southern Ryukyu, the delay is much further, is much longer compared to the Sumatra. Here is the signal that sample the subducting slab, indicate a low amplitude onset, and then a delay of high amplitude arrive later. While the one that non-sample slab, high amplitude arrive immediately. And the delay indicate a couple of seconds of this signal. Here the station distribution is very close to each other. However, some particular station, especially located above the 10 kilometer above the slab or 20 kilometers above the slab. So within this region indicate a very sustained delay of P and S wave arrival. And the dispersed signal on the frequency domain is indicate the same as the Sumatra. However, as I mentioned earlier, the amount of delay is much larger. So on the left-hand side is the signal that sample the slab. If you see here, where the P arrival, the onset is located at 5 seconds. At 5 seconds, the amplitude is very small, but the big amplitude arrive 1 second after that. So it's already 1 second delay for the signal itself. Then the energy of the frequencies can go really high frequencies until 220 hertz. You still have a very high energy. You can observe this one have about more than close to 2 second delay. So this is a very thick oceanic crust observed at the southern Ryukyu subduction zone compared to the Sumatra. While the one that did not sample the slab, you can see the onset immediately impulse, have the impulse response shown like this one and this one. And the high frequencies arrive earlier than the low frequencies. So this one did not have any information about the slab, while this information have the information about the slab and the oceanic crust. So for the conclusion, the Sumatra subduction zone observed about 2 until 4% delay of the higher frequency energy. The southern Ryukyu subduction zone observed more than 5% delay of higher frequency energy. So it's been suggested to have a thicker oceanic crust being observed at the southern Ryukyu subduction compared to the Sumatra subduction zone. So that's all for my presentation. Thank you very much.
Okay, thank you very much, Dr. Haikal Hariri, for your presentation, but our time is over, so I can't collect your questions. Now the time for our room presentation is over, and I really appreciate for all the presenters who have delivering the great presentation today. So please applause around for all of us. So now it's time for us to join back the main room, and we will have the keynote speaker from Dr. Morelia Urlau. So thank you so much again. Thank you very much, and see you next time. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Yeah, please join the keynote speaker at this late afternoon, because the topic is very interesting. It's about the submarine landslide. So see you guys on the main room.
Yeah, thank you for the information, Dr. Haikal.
Bye-bye.
Bye-bye. Thank you. Ibu Sri Agustina. See you to the next
Dr. Sabrina,
seminar.
see you next time. See you in the main room.
Yeah.
Yeah.